Lecture 11, Sampling ADCs and DACs. Quick announcements, practice midterm has been posted. I won't post solutions, so please solve it together, find solutions to it. I won't provide them, but if you have questions, come and ask me during the office hours. I'm happy to explain you how to solve certain problems. Homework 2 is due now. If you don't have done so yet, please put it up here in the front. Homework 1.3 and 1.4. Some of you have not posted the pictures yet. Please post them by Friday. I really want to correct them before the midterm so we have them done. Yes?
We need a picture for 1.4.
Yes, please.
That means with the LED on.
Yeah, just the whole board populated.
I just didn't see that on there, so that's why.
It's possible that I didn't put the text in there yet.
You want
Yes.
to make sure that it's working. Good.
Could be working, does not have been working, as long as it's assembled. That's because it's a static picture. I mean, or if it's blinking LED, you can take a little movie of it. I mean, that's fine too. But I think Canvas has like certain upload limitations, so I'm not entirely sure how much you can actually upload. All right, minute quiz. Last week we covered serial buses, so it will be on serial buses. Let's do head is minute quiz. All right, so tail, no? Head is minute quiz. It's tail.
Okay.
It came off, I'm sorry. Sweaty hands. All right, no minute quiz. Which serial protocol can achieve higher bandwidth? I2C or SPI? Why? I2C can have flexible clocks. It's not entirely.
I2C only has 2 wires.
Okay, I2C only has 2 wires. SPI has 4. That's still not really why it's faster. Yeah? Yes. Correct.
But doesn't I2C also have an address?
It does have an address in there, so yes, it probably also has more overhead. If that's what you ask, yes. But that's really the limiting point, right? I2C is physically limited to 3.4 megabits per second. You can't really go much faster than that. Or else you will just have, like, because of the slew rates that I explained last time, it just won't go faster. While SPI can easily go up to 50 or even more megahertz, right? So it's a lot faster. So overhead and clock speed. Okay, last time we just stopped before the Universal Serial Bus Protocol. Today we're going to finish that before we jump into ADCs, DACs, and a little bit of sampling theorems and stuff like that. All right, USB is already pretty old. USB 1.0 was released in 1996. It has a data rate of 1.5 megabits and 12 megabits. 12 megabits was the old full-speed devices. In 1998, it already was superseded by USB 1.1 because there were a couple of issues they found in 1.0, so they fixed them in 1.1. And USB 1.1 was the thing that was like around for quite a while. Before USB 2.0 in 2000 came out, and it wasn't immediately adapted, but eventually USB 2.0 is what we use these days probably most of the time. USB 3.0 came out in 2008. Who has a USB 3.0 device at home? So about like a third, maybe half. What type of device do you have? Hard drive, right? That's pretty much what everybody uses this for. External hard drives, because it's nice and fast. It actually has defined speeds of up to 5 gigabits per second. Realistically, we can achieve about 3.2 gigabits per second. So we aren't really at the 5 gigabits yet. What could be the issue? And why has it taken almost 4 years for the adaptation of USB 3.0? Right? Who bought the USB hard drive last year? I certainly did. Somebody 2 years ago or earlier? Yes? You're a quick adopter. Probably most people got it probably last year because only now laptops really get available with USB 3.0s, like they're very widespread. What could be the problem? Yeah? AGP was out there before, PCI Express, right? There are super fast ones. SATA is out there since a while now. So that's not only. It's not the memory interface only. So hard drives haven't really been fast enough. That's a good one, yes. There's another problem. At these kind of speeds, signals become really tricky to deal with. And it's actually really hard to make a system that runs at 5 gigabits per second, especially if you have to go through plugs and stuff like that. Your cable quality has to be right. The plugs have to be appropriate. Or else every kind of little thing there can destroy your data rates. Yes?
So when they say maximum of 5 gigabits, what's like the model? I mean, what's...
It's defined up to 5 gigabits per second. So at some point, it's, for example, cable length that they standardize to. They say, this is the cable length, and then you just can't go faster because of the round-trip times you achieve. Signal quality is a big one. Anything else?
That also doesn't take into account negotiation and other protocol overheads.
Yes. This is the raw data rate.
Yeah,
That's physical raw rate.
zero.
And we're going to look into what the protocol really is at the raw and what the different layers are of USB in a second. So the USB system design consists of a multitude of different levels. At the top level, it's a hierarchical tree that can have up to 5 levels. So you can have USB hubs in between, which are basically branches, and from there you can connect new USB devices or more USB hubs. But you can only have down to 5 different levels. So how is that defined? Well, sometimes your computer already has a hub inside, right? If you have more than 1 or 2 ports, you actually already have one hub. That's the first one. Now, sometimes you can have what's called logical devices. For example, this webcam over here. It has 2 USB functions on there. So it has 2 logical devices inside. And internally, they're connected through a USB hub. So you have to be careful that if you connect too many USB hubs to each other and then connect one of these devices in there where you don't think it actually has a USB hub inside, it could be that it doesn't work anymore because you exceeded the 5 levels that you can have. USB can also have up to 127 different devices. If you have more than 127 devices, it won't work anymore. Sometimes it even starts stopping before. We did some tests in our lab where we could barely get 70 devices enumerated on one of the USB buses because the software in the back end actually did not accept more of them. So physically, the protocol can probably handle it, but the software, the drivers could not. So what comes after the logical devices? Well, for logical devices, we have then logical pipes, or also called endpoints. And you can have up to 32 endpoints per function. What does that mean? You have 16 endpoints going from a host to a device, and 16 from device back to the host. One of these is actually reserved. That's always endpoint number 0 in both directions. That's for control and configuration of the devices themselves. The other pipes or endpoints can be used for communication. And each one of them can have 2 different types. There can be streaming or messaging. Streaming is usually used for bulk transfer and can go very, very fast, while messaging is a bidirectional path. So there, an endpoint is not going just from one direction to the other, but over the same pipe, you can actually go back and forth. But they're a lot slower. Okay, so let me recap this again. You have a hierarchy of tree in the physical sense where you can have up to 5 levels. You then have logical devices connected to your USB ports. These can have different functions inside the logical devices. Each function has up to 32 pipes, and the pipe can have 2 different types, streaming or messaging. Okay, so let's go through this and see what we find for these different devices here. Yes?
What does it mean we have a 5 hierarchy tree?
So if you have hubs in between, you can have a depth of up to 5 of them before you have to have the device. You can't have 6 hubs connected to each other. The last hub will not be enumerated anymore. Okay, so let's see which one of these devices has streaming or messaging pipes. Let me repeat, streaming is unidirectional isochronous. That's, for example, if you need guaranteed data rates. You can have interrupt or with a bounded latency. Basically, those are devices that have to react very quickly to a certain event, so you have them interrupt driven. Or you have bulk transfers where they try to use as much of the bus as available, but it's not a guaranteed data rate. Messaging is a bidirectional control transfer, so over the same connection you can go in both directions, but it's not guaranteed and it's pretty slow. What do you think does, let's start with a flash drive over here. What does it use? Messaging? Why would it use a messaging? Bidirectional control transfer. So okay, we want to certainly read from a flash device, right? And we want to write to a flash device. How do we want these reads to happen? Slow? Fast? Bounded? Probably fast, right? That's probably the key here. We don't really care if it takes a second, but as long as we transfer a lot of data, that's good enough for us. We don't need a guaranteed bandwidth, right? We just want all the bandwidth we can get. So what we probably have is two different pipes that are both bulk transfers, one going from the device to the host, the other one from the host to the device, right? Okay, hard drive. Same thing, right? Bulk transfer, you want a lot of bandwidth. Keyboard. Interrupt. Could be interrupt. It's actually using messaging protocol. USB HID protocol, it's the human interface devices. They're using the messaging interface. Because we could wait for a long, long time on this thing. And then all of a sudden somebody presses a button, so a message is sent over to the computer. What about this guy here? USB serial. Sorry?
Why do we need bidirectional or keyboard?
You don't really need it, but that's how they implemented it. Could be just one way, I agree. Yes?
Why do we not because it needs interrupt and also one
You probably could do it with a streamed interrupt interface, yes. But it is actually a messaging interface. It's messages that go back and forth.
messaging also we have interrupt?
No, but it's a message that goes over. So as soon as you receive the message, an action happens. So it's not exactly like the streamed interrupt one. USB serial. Isochronous? Why do you need a guaranteed data rate?
Because you're setting it, right?
You do set it, I agree. But you don't use it all the time. What's a typical isochronous transfer? A guaranteed data rate, yes. Webcam, audio devices, they need a guaranteed data rate, or else the video starts to stutter. Right? If all of a sudden a bulk transfer comes in, you want to guarantee that that audio and that video keeps going. So those are probably isochronous devices. Serial is actually also, again, messaging that go back and forth. Over the same bus, you have messages going back and forth. Okay, going one level lower down, what does the signal look like that we have out there? Well, we have 4 different speeds, right? We have 1.5 megabits, 12 megabits, 480 megabits, and 5.0 gigabits per second. That's the speed at which the signals can go over, or the clock rate that it can actually have. Encoded, the whole thing is in a differential pair. Usually when you look at a footprint of a USB connector, you see a D plus and D minus. That's for devices before USB 3.0. You had one differential pair that actually was a USB bus. Since USB 3.0, they added a second differential pair. So now you have one pair that goes from the computer to your devices and another one from your device back to your computer. So you actually have 2 additional wires that you have in USB 3.0. Yes?
Isn't there a version of the USB 3.0 connector that only has one pair?
I'm not sure. Are you sure it's still USB 3.0? Or is it a backward compatible 2.0 type? Or it could be that it's a lower rate one, USB 3.0 standard. That's something in between. But I know to get to the full speed, you have 2 differential pairs in USB 3.0. So if you actually ever look at a plug of a USB 3.0 device, and if you look in it, you see on the top, you see the 4 regular ones that were already there for USB 3.0, but on the other side, there are now all of a sudden also a couple of more pairs of USB devices that you can plug in. All right. Looking at what's going over that differential pair, the encoding that is called differential signaling with non-return to zero inverted. Long name for something that's really not that complicated. Down here, we have a D- and a D+ signal. Remember, they are differentially encoded, so if one of them is high, the other one is low. USB then defines 2 different states. The state K, where the D+ is low, D- is high, and J, where D+ is high and D- is low. Right? So we have a K and a J state. In addition to that, they have a special state 0 back here, where both lines are low. Remember from I2C, there is like the stop sequence. This is the stop sequence for USB. If both signals are low, it means abort this transaction, or this transaction is done, or it's aborted. Okay? So we have K, J, and zeros. Now the encoding works that way that we have differential signaling, so that's the KJ, with non-return to zero inverted. Non-return to zero means that we have a transition if there is no transition. So what does that mean? If we have a J going from K to J, we have a 0, no transition, JJ becomes a 1. Transition to K is a 0, no transition becomes a 1, no transition becomes a 1, transition becomes a 0, no transition becomes a 1. So the inverted comes that usually non-return to zero encoding would be 1, 0, 1, 0, 1, 0. This is inverted, makes it 1, 0, 1, 0, 1. So that's the big difference. But all you really need to remember is that there are 2 states, and then the encoding sits in, does the state change or not? That will define if you have a 1 or a 0. Not in what particular state your bus system is in. Any questions to that? Yes?
What's up with the slight change in non-transition? Where there's like a quarter of a volt drop.
From here to here?
No. In the
Where it stays the same.
This one here?
that.
That's what happens if you go through a channel. If you try to, if you can send over sine waves very easily. But if you try to keep the sine high, it will start bouncing and looking like that. Right? Because this is basically a no transition. That's what will happen. It will swing, but it wants to go back, but just doesn't because you hold it back up. It's very typical if you actually look at signals on the physical layer. No? Okay. Yes?
So is this decoded on a hardware level?
Yes. Remember last time we talked about SPI, which is not certified or defined at all, and you can basically do whatever you want. In USB, you actually have to get certified. So it's very, very defined what's actually happening, what type of data is going over, what the clock rates are. So yes, everything is basically done in a chip. And there are chips out there, and we have a bunch of them if somebody wants to play with them, that basically provide you a SPI interface to your microcontroller, and on the other side is just a USB host controller. So that it generates the right signals, decodes everything, and then what you do is you talk through it like a SPI peripheral. You can generate USB devices. Yes?
What's the advantage of a differential pair as opposed to sending a signal on one wire?
It's noise reduction. The nice part is, so why do you have different differential pairs that are most of the time also twisted to each other? If there is external noise that comes in, it will affect both lines the same way. So both of these lines will be shifted, for example, up or down if there's noise in there. So if you take the difference of the two, you actually just remove the noise out of it. That way you can go further distances at higher data rates without having to have a fully shielded cable, for example, to try and avoid external interference. Yes?
Go over the encoding one more time.
Sure. So there are 2 states, K and J, right? K state is D minus high, D plus low. J state is D minus low and D plus high. What happens is we have no transition. That's basically the start of the packet, is this particular sequence. Then it goes from K to J is a 0 because we have a transition. J to J state, no transition, it's a 1. J to K is a transition, it becomes 0. KK, no transition 1. KK, no transition 1. KJ, transition 0. JJ, no transition 1. JK, transition 0. Make sense? And then comes the 0, 0 state, which basically indicates that data done. Yes?
What's the point? Why did they bother doing this only invert if it stays
Again?
They invert it if it stays the same, but only on the second repetition. You know, like KKK, 0, 1.
It's the way this encoding scheme works. So if you want to go and look into what the advantages are of this encoding, it's probably faster detection of errors and a whole bunch of other stuff that probably comes with this encoding scheme. I would have to think and read up on it again too to actually figure out why they exactly chose non-return to 0 with differential encoding. And on the sense differential encoding, I'm not entirely sure why they took the other one. Yes?
So, I mean, obviously, explain me a synchronized system, so it has to be synchronized with some clock, but which clock is it going to be running off of? Because you might have two different devices with two different clocks through the USB, right?
It's...
But like a webcam would have a clock on it.
Yes. It's an asynchronous protocol.
Okay.
So what they have is USB is a standard, and they define what type of clock you have to have on the other side, or how precise that clock has to be.
But which other side, depending on
The device.
Okay.
So the device has a clock in there. There's no clock signal going over.
Okay.
So it's like not USB. That's what we're talking about. UART. So the other side has to have a clock that actually can decode the whole thing.
Okay.
And I have actually notes down here. For speeds up to, at 1.5 megabits per second, they allow you a plus minus 15,000 ppm clock. So very easy to meet. It can be very inaccurate, and you can still easily decode what's coming over.
Okay.
So then when you go faster to 12 megabits, it's 2,500 ppm, plus minus 2,500. And at 480 megabits, it's plus minus 500 ppm clocks. So pretty much any crystal can meet the plus minus 500, but RC oscillators or on-chip oscillators becomes a little bit more difficult to do. And I'm pretty sure if you go to USB 3.0, it's even more stringent on what type of clock you have to have in your device in order to decode what's actually going over.
So is there a handshake before the encoding stuff goes on, so you know which?
This one here, this KJ, KJ, KJ transition always comes at the start of a packet.
Okay.
So from there, you can probably find out how inaccurate your clocks are in figuring out what's going on.
Okay.
And maybe correct even for it. Yes. Yes.
In USB, we have 4 lines.
Before 2.0, or before 3.0, it was 2 lines plus power and the ground. So it was 4 lines in total. With USB 3.0, they added 2 more lines. So there are now 2 differential pairs and power and ground. And there might be that there are other, like the standard is pretty big, there might be that there are other possible configurations, but this is the standard configuration. Okay, any other questions? Any other questions for serial buses in general?
Can you talk about the packet ID there? The acknowledged signal?
There are a lot of different packet IDs. So if you actually go into details of USB, it's an extremely complex protocol. If you ever try to, like, it becomes now very common that you have microcontrollers with a USB interface. And writing drivers for them is not fun. They are really complex. Like, there's all kinds of different enumeration, different type of packets, different degradations that you have to have, and handshaking mechanisms. I mean, the driver itself is just a beast. I have only done it once, and I just used TI's USB stack and fortunately got it working. But I cannot claim I know how USB works in detail itself. So there are a whole bunch of different messages. This one here is, for example, a NAC implementation. There are ACK implementations. There's a whole bunch of different types. Basically, in this, all of this encoding, it defines what type of packet it is, like isochronous, how configurations get set up, and everything. Okay. In that case, let's move over to sampling. And in this case, I quickly want to do a demo on what kind of problems we can have when we start sampling a signal. All right. Everybody's probably familiar with this interface by now, right? It's our small little logic analyzers. So I'm generating a signal over here. Now, let's start sampling it. There we go. Okay, something came out on channel 0. What type of signal do you think is this? Can we tell from this what it is? Yeah? A PWM signal? Could be. Goes up and down a little bit. Yes?
Plus the logical measures high and low state.
Okay, it does measure only high and low state. I'm mostly interested in the frequency, actually, right now of this signal. So it could be a PWM or it could be a frequency. So let's, if you see here, there's like a wide line. So let's zoom in here. Oh dear. That's odd, right? Well, okay, maybe we don't sample fast enough, right? So right now we sample at 8 megahertz. Let's increase this. Let's say, let's go to 16. So we double the system. Oh, there we go. It's just a square sign, right? Let's see what happens if we go out. Oh, wait. That's odd, right? There are like huge steps in there of just highs. And in between, it's a nice square wave of what? 8 megahertz right now. Remember, there's 8 megahertz. And we sample at 16. Okay, so let's see what happens. Let's go to 40 megahertz. Oh, that thing disappeared. Oh, no, not really. Still somewhat here, right? That's odd. Let's sample this again. Changes a little bit. All right. Double again. Let's go to 80. Still a little odd, right? High periods, and then we go in here, it's gone. But over here, it clearly, oh, it's a 40 megahertz signal. All right, let's see what happens if we go to the full speed. So now we sample at 100 megahertz. And if you look around, okay, here it says we have a 50 megahertz signal, then we have a 33 megahertz signal. What's going on here? But at 8 megahertz, it looked like very strange. Looked like a PWM with some weird transitions in between. Then we went up to 16, it told us it's an 8 megahertz signal. Then we went up to 40 megahertz, where it became really strange. And now we are at 80 and 100 megahertz, and it still can really tell us what's going on here. Could be superimposed signals, yeah. So some of the problems that you start to have if you want to work with real signals in real reality, you actually need to know what the signal is or what you expect before you can set your either logic analyzers or your oscilloscope or configure your ADCs in your embedded systems. In this case, I'm actually generating a 40 megahertz signal using this function generator here. And what happens is, if we have a 40 megahertz signal, right, that goes up and down at 40 megahertz, and if we sample it at 40 megahertz, by chance, we can always just sample it when the signal is either low or either high, right? Well, let's go back to this one. 40 megahertz. So we have a period where it's high, then it's a period where it becomes low. Now from this, you could actually calculate how different the two clocks are from my Celia logic analyzer and this device here. Why? We sample at 40 megahertz here. We generate a 40 megahertz signal here. But remember, they're not the exact same clocks, right? They're drifting with respect to each other. So what happens is one of them will have the 40 megahertz. Let's assume that one is perfect 40 megahertz, and the Celia logic has an internal crystal that says it's 40 megahertz, but it's not really. Maybe it's a little faster or a little slower. So for a long time, it will sample it at high, and then all of a sudden it goes to the transition region where you see something like this, right? Where you hit sometimes before, sometimes right after, before, after, and then all of a sudden you are past it, and then you sample the clock at the low frequency. So looking at the width of this signals here, you could figure out how inaccurate both clocks are and how much faster one of them is compared to the other. So then how fast do we have to sample in order to figure out what's going on with our signals? More than twice, exactly. We're going to look at that. That's what's called the Nyquist theorem. Nyquist says that if we sample a signal more than twice its highest frequency content, then we can reconstruct it entirely. Okay. Yes? Let's go to 80. What is 80 megahertz? From 40. It's exactly twice. You have to go faster than twice. So if we go to 100, we are exactly twice now. And we can now, no, we are more than twice. So we can say that on average, this actually will probably even out to a 40 megahertz signal. In addition to that, we are also having a square wave. If you look at the frequency content on a square wave, it has very, very high frequencies involved. Right? What we would have to do is actually have a sine wave. So I can switch it over to a sine wave. I have not tried this out yet, what happens, so let's see what happens. Oh, it's the same thing. But on average, this will probably give you a 40 megahertz signal if you would average it out. All right. Any questions on this experiment? On what you do? So sometimes be careful when you start sampling any kind of signals. Like, make sure you sample at the right frequency compared to what your logic analyzer is set to, or in that respect also your oscilloscopes. If you try to look at a 200 megahertz signal using a 60 megahertz bandwidth scope, you probably won't see anything or just something that's completely wrong. Okay. So we live in an analog world, right? Everything we do and interact in the real physical world are analog signals. So we need to convert these analog signals somehow into an electronic signal. And a device that's converting energy from one state into energies from a different one, it's called a transducer. Oftentimes, when you hear transducers, people think it's a sensor, but it's not necessary. But most of the times, a sensor is a type of a transducer. It takes energy in one form and makes it into another. But transducers can also be used for other things. So what does a transducer do? Well, it converts from one thing into something else. So it takes some sort of output in a volts, and for example, in this case, it takes temperature gradients and translates this into an output voltage. Most of the times, the transducer has also a nice little curve that they give with you, which would make it a relation between Celsius, in this case, and the voltage at the output. So for example, in this case, we find that the voltage of the temperature is 0 point something times the temperature plus 0.986. That's what this particular transducer would do and produce. So if you give it a temperature, it would generate a voltage for you. So now how can you, yes?
Could you give me an example that it's a transducer, but it's not a, for example, a sensor?
Well, yeah.
That's not a sensor.
But you could use it as a sensor. The question is probably always like, do you use it as a sensor or not? It's a good question. A generator, for example, is a transducer. It takes mechanical energy and produces electrical energy out of it. Not necessarily used as a sensor. You could use it as a sensor to figure out how much mechanical energy is actually produced, right? If you measure the output on it. But usually you use it to generate energy, electrical energy. So, wasn't there no example given? Nope, all sensors. Or photocells, like solar panels, or also they take photons and generate electrical energy. Yes?
So could you say LEDs because it takes
Yes.
electrical energy into light?
Yeah. It's also a transducer. Oh, that's a good one. That's not a sensor.
You have a speaker on there.
A speaker, yes.
What is
Yeah, but then it becomes a mic. Yes, I agree. So yes, makes sense?
Yeah.
Okay, so a transducer is something that takes one form of energy, produces it differently. Okay, so how can you use this now in a circuitry? Everybody knows what a voltage divider is? All the C's and E's are, yes, of course, yeah, this is what we learned. Do we have CS in here? CS people? Yes? Do you know what a voltage divider is? No? All right, you will learn it now. Because many sensors use voltage dividers to actually give you an output signal. So a voltage divider is nothing else that divides a signal that you have into half or a third or something like that. The most simple circuit is something like this, where you have two resistors, right? You have a voltage up here, two resistors, and then you can find the voltage over here by 5 volts times the resistor, RR, so the resistor down here, divided by the total resistance. So the output here is basically the input voltage you have times the resistor divided by the total resistance. That's a voltage divider. Okay? Now, what happens if RR changes its value depending on, in this case, the incidence light, right? Depending on how much light comes into this resistor, it will change its value. So what will happen is the output voltage over here will start varying too, right? Depending on how much light comes into your device. Now there are a couple of problems that are coming up. First one is, in a voltage divider, if you are in EE, you should know that as soon as you hook up something to this voltage over here, you change the equations. So what you want to do is you want to buffer it over here before you start measuring the voltage itself. So you can have just a unit buffer on there, which we'll cover in a second what this really is for everybody who doesn't know. So you want to buffer whatever is on here in order to not change the voltage divider. In addition to that, there's capacitance in the system. So what will happen is, depending on how fast this will change, it could be that this output voltage here has slightly a swing and it takes some time to actually adjust. So what type of forms of different sensors can we have? Well, we can have force sensors. They can measure a force and produce an electrical current. We have sound microphones or sonar. Some of them work with piezoelectric effects, where you have a piezo crystal that you squish and then generates a voltage. Or you use a coil and a metal that you go through it and actually can measure what this produces. We can have position microswitches, shaft encoders, or gyroscopes. Acceleration we can measure using pendulums or MEMS accelerometers. We can also monitor different things, for example, a battery. If you want to know how much energy is still left in there, you can measure its voltage and you get a hint of how much energy is still stored in the battery itself. Motor currents, you can monitor using measuring voltage, or we can look at different fields. We can have antennas for magnetic and electric fields, and we can have Hall effect sensors, etc., etc. They are all transducers. They produce usually a voltage depending on a different input signal. So what we want is really something where we have a physical phenomena, we have a little black box, and out comes the most preferred case an engineering unit, right? That's what we work with. We want to know how much Celsius we have out there. We want something in an engineering unit. What we get, though, is something like this, where we have a physical phenomena, we have some sort of sensor that produces voltage or a current or a frequency. We then take what's called an ADC, an analog to digital converter, that will take the voltage and give us a number, a digital number out. Now this digital number is just a number, it doesn't have any units yet. So we then have to use software to translate this ADC count into an engineering unit to understand what's actually going on. So let's start over here and with the ADC to understand a little bit of what's going on. Assume we have this signal here, f of t, changes over time. What we now have to do is we have to sample it over time at a certain rate ts. Right? That's kind of what we did before with the logic analyzer. We told it to sample it at 1 divided by 40 megahertz, 1 divided by 40 megahertz. That will give us all these different samples. Okay. Now these samples will tell us what the form of this system looks like approximately. Will give us these little dots here in digital counts. And then we can use formulas to find out again what the actual unit was before. So what range should we use, right? If we measure something like this, we need to tell, okay, how much do we actually expect on the input? If we take a system like this and we take our signal and we say we are only interested in between VR minus and VR plus here, well, what will happen is we cut off certain amounts of the signal that we won't see. Similar to this one here, if we choose VR minus and VR plus too big, then we don't get enough resolution on this signal. Remember, we have a digital system, so we have a certain size that we can refine. If we take our range too big, we can't find out what our signal is. What we really want is find a VR minus and a VR plus such that we maximize the content of our signal to get the best resolution that we can find using our ADCs. So, two things that we have to talk about, resolution and quantization error. Resolution is what our ADCs can resolve. So for example, in the case of the MSP430, if you have a 12-bit ADC on there, you get 496 different values. 4,096 different values, thank you. So if we take the range of our ADCs, VR plus minus VR minus, which would be the range of our ADC that we're looking at, we can get a step size of the range divided by 4096. That's the minimum amount of voltage that you can refine and find out in your system. If you have a signal that's smaller than that, you will always get the same ADC count and you don't know what's happening. Quantization error is exactly the error that your real signal is something else. It's maybe in between two different digital counts. So what will happen is if you have the measured voltage over here versus what you think it is, versus the input voltage, you will see that you get digital steps, right? You have -4, -3, -2, -1, your digital steps that happen. But in reality, you actually input a signal that's real, that's changing all over the place. So what will happen is that you make an error in your quantization, in your measurements, that's usually 1/2 the LSB. So what happens is in between here, the transition maybe happens in between half the voltage. So we will have -4 over here. Then we get the actual voltage is now becoming -3.6. So we make a minus error in our actual quantization. And then it jumps up to 3, but we are actually not at -3 yet. So we are too high in our voltage before it goes down, down, down. Here we hit the perfect spot where we don't have an error, etc., etc. So that's what the quantization error is with respect to a real signal. So then how do you get now from ADC counts back into what voltage that you have? Well, we can find the equation that the ADC counts is 4095 times the input signal minus your negative reference divided by the span of the range that you have. You can now refine this and actually flip it around, and what you get is Vin is equal to the ADC count times the span of your signal divided by the size of your ADC. Make sense so far? Right? Yes? They don't have to be negative, but usually you have two reference voltages. The minus is the lower one, the plus is the higher one. So they can, for example, be 1 volt and 2 volts, right? Sometimes, yes, the negative voltage can be a negative voltage, like it goes into the negative. But more often it's something positive. Most of the times, VR minus is actually ground, and VR plus is VCC, but that's not always the case. Sometimes you can actually change it and give different reference voltages. So this is how we get from ADC counts to voltage. Now, how do we get from voltage to engineering units? Data sheet, yes, data sheets. The data sheet will usually tell you what kind of voltage you get for a certain engineering unit. So for example, in the case that we had before, for a temperature sensor, we have the voltage of the temperature is this. So we get the temperature by taking the voltage that we measured on our ADC minus 0.96 divided by this number. Bam. We get temperature out from an ADC. Questions so far? Did it all make sense with the reference voltages, what they mean, how to use them? More or less? So why do we need reference voltages? Why don't we always take ground and VCC for the ADCs? Why would you ever want to use something else? Not all sensors run at VCC, yes. And sometimes you're interested in a signal that's much smaller than between ground and VCC, right? What you then can do is you can scale down your range of your ADCs and get a higher resolution within that smaller voltage. Okay. So a couple of things about sampling and math in your embedded systems. Formula up here were from the last slide, right? How we convert this over into engineering units. Now, assume that you have a 16-bit microcontroller, right? Assume also that VR plus in this case would be 1.5 volt. VR minus would be ground or 0. So implementing this in C, Vtemp is the ADC count that we get divided by 495 times 1.5. So the temperature becomes Vtemp minus this number divided by this floating point number. Do you think you will get the temperature out of this? The result will actually be 0. All the time, no matter what you measure. Yes. There's an integer division in here. Right over here.
So add a 0.0.
You could add a 0.0 to this number down here, and you would be fine, because then it becomes a floating point. But if you do this stuff in your microcontrollers, be careful of what you do and how you divide. What you could also do is first multiply by 1.5 and then divide by 4095. However, at the same time, be careful of using floating points. Because if you don't have a floating point unit, what will happen is GNU or the compiler has libraries to implement floating point calculations, but they are extremely expensive, which means that they take a lot of computation power in order to do something. So in order to do something quick, you want to stay with fixed point operations. So how could you implement this up here in a fixed point implementation and still keep it reasonably accurate?
Shift right.
4096.
Sorry?
Change that to 4096.
4096. No. Fixed point means that you do fixed integer calculation,
right,
and not a floating point. So
right, but you just shift it.
you could do a faster shift, but still you get 0, right? No matter, because ADC count is always smaller than this. If you just right shift it, you just emptied your whole register out. That's exactly the problem. So how could you solve that? Yes? Multiply it by 10,000. Why would you multiply by 10,000? Okay. Okay. And then you divide it by 10,000 again, I hope. Yes. So you have to start playing tricks and shifting the decimal point around, right? So for example, in this case, what you could do is first, you have multiplication by 1.5. So what you could do is multiply it by 15 first, right? You get a higher number, an integer. Now the problem is, you could divide it now down by this number, and then divide it by 10. You will probably get a very small little integer, potentially. Or you just say, okay, instead of having integer counts, we say it's now millivolts, right? So yes, you could multiply this first thing by 1,000, and then you get millivolt counts. And then you have to adjust this number down here again in order to do another calculation. But you can basically shift the decimal point around as long as you keep track of what units you're actually calculating in, if you want to avoid floating points. Okay, any questions? Good. how do we choose the sample rate? Like we saw it before in the little demo, right? If I choose the wrong sampling rate, what we can come up with might not exactly be what the signal is that we are having. And we talked about it. It's the Shannon-Nyquist sampling theorem. It tells us that if a continuous time signal f of x contains no frequencies higher than f max, it can be completely determined by discrete sampling taken at a rate of f sample bigger than 2 times this f max. So how can we deal with that, right? I mean, this is kind of difficult. You really need to know what's going into your ADCs, or else you can't really determine your sample rate. So what they do is, for example, for humans, we can process about signals from 20 to 20 hertz to 20 kilohertz. So we say an audio signal that's sampled or an audio CD at 44.1 kilohertz is probably as perfect as we can reconstruct. Now, yes, audiophiles probably would say, no, we need 96 kilohertz samples, but this is kind of what we need. More than that is really not very useful for our hearings. Another thing that can happen is what's called aliasing. And that's exactly what Nyquist says. You can have 2 signals that look exactly the same if you sample them. One of them is just at a higher frequency than the other. Blue curve here and the red one get sampled at the exact same time. You can't tell if it's the blue low frequency signal or if it was a higher frequency signal that was just by chance sampled at the same instances. This is what's called aliasing. In order to avoid this, oftentimes what we do is we add a low-pass filter into our system before the ADC input to make sure that we don't get any kind of frequencies that are too high, because it could really corrupt our measurements themselves. So how do low-pass filters work? They're really fairly simple. I just put them up here for those who have never used a RC filter. The formula is this one. So we have the output voltage over here is the input voltage on this side times 1 divided by the square root of 1 plus omega squared r squared c squared. If you plot this as a spectral plot, it will look something like this, where this is the log of the W, and the ratio between the output and the input looks something like this. And the 3 dB point is at 1 divided by RC. So that's where the power inside of your signal got halved, right? It's a log scale, so halving is 3 dB. So now let's do a quick exercise. Let's assume that we find an RC pair that can produce us a half power point at 30 hertz. So you are only interested in signals that are lower than 30 hertz. What type of RC would you take? How do you even define this now, right? We have 2 unknowns, R and Z. How do we do that? Get together in teams of 2 and discuss this quick. Okay, how do we go about this? We have 2 unknowns, R and C. What do we do? Pick a value for one of them, exactly, then calculate the other one. So which one do you pick, the R or the C? Why would you pick the C? Sorry? Correct. Less choices. Resistors you can do in pretty much any value, or else you can at least get a good combination of them and put them together. For Cs, it's a lot harder. So first you pick a C, right? and then you calculate the R out of it in order to get the half point at a certain frequency. So how do you do that? We have 30 hertz. So what's the omega of 30 hertz? Sorry? 60 pi? Sounds about right. So we have 60 pi is equal 1 divided by RC. Now, what value do you choose for C? What would you go with? Sorry, 1 microfarad? 10 micro, yeah. You just pick something, plop it in there, and calculate the R. And then hopefully it's an R that's a standard, and then you can buy it too, else you have to start combining the different R's together. Okay, any questions to this? Making a filter? Could you do it in your homework? Not homework, in the midterm? If I ask this? Yeah? You too? Yeah? Okay. Yes? Could you do this in software? Yes, but you wouldn't want to. It's a lot of calculations you would have to do. Yeah, you could. Yes, but you could still oversample your signal and then filter it in software. So in theory you could. But yes, the goal of this particular exercise that we just did is you put a low-pass filter in front of your ADC in order to avoid higher frequencies going into your ADC at sampling. Yes, that's right. Once you have done this filtering, then you can get it out again in software because you filtered out everything that was higher. Was that? Yes? Okay.
The cap and the resistor are way cheaper than buying the faster ADC and hiring the DSP engineer to write the FIR filter to do that.
Yes, but you could do it.
You could.
You could do it. Okay, another quick technique before we will actually stop for today, and we'll talk about ADC and DAC architectures next week. The technique that you might have heard of is called dithering. So what do you do if you need more resolution than your ADC can really provide? And you might have seen that before in images. This is an old type of a GIF image that was just like thresholded. And you can now very clearly see the different thresholds that happen. And then there is a technique that's called dithering. And what will happen is something that looks like this. Now the nice part is this looks a lot better, right? But it now wasn't sampled at exactly the right points. And it was actually noise injected into it before it got sampled again. And that way you get a much nicer looking picture. So how does it work? Well, assume you have a signal, a sine wave in this case, that you sample with your ADC. This is if you look directly at one sample that got sampled all the time. Now what we could do is we could just oversample by 50 times, for example, and then take the average of these 50 samples, right? Unfortunately not, it would look something like this. So where you had these transitions happening, maybe there, sometimes you had one that was up and was low, so now you get these like softer edges on the corner. Now assume what we could do is actually inject white noise, right? That just gets added to the original sine wave. If we add white noise on top of this, and we sample it, and look at each and every sample, we will get something like this. So now, because of the white noise, sometimes the sample would be higher, sometimes lower, higher, lower. And the key here is that the chance of being higher or lower actually depends on the signal on where it was at. Now, because it's white noise, if we average it, on average it will be 0. So what happens is if we average this one out, we will get out something like this. It's a lot smoother, even though we only sampled it in certain digital intervals. Because we added this noise, we sometimes pushed it over the edge on the top and the bottom, and that way when we average it out again, we actually get the signal out without having to use a higher bit ADC. Okay, there are lots of other issues. Sometimes you need an anti-imaging filter because ADCs can have images and stuff and very crazy things that happen. Most of the time, low-pass filters will help you with that. Cost and power of ADCs oftentimes play a role. The faster your ADC goes, the more power they will draw. And sometimes you don't even need an ADC. If you're lucky, your sensor is available as a frequency output, and that way you just count a frequency. And that, as you know, that's a lot easier than getting an ADC sample in there. Or sometimes you can generate a PWM signal to, for example, control a motor. You don't have to actually generate a voltage to drive it. All right, next week we're going to talk about DACs and ADCs and architectures before we finish up and prepare for the midterm.